So last time we looked at limits, and this time we're going to jump into the limit definition of the derivative, like I said we would look into last time. So given a problem that says find the slope of the tangent line at x equals 1, and let's pause, if you don't know what a tangent line is, it's kind of this line that just grazes the function at a point. So if you look at our first point, it's the line that grazes the function is this horizontal line. At our second point, the line that grazes the function is kind of this downward sloping line. And asking for the slope of the tangent line is exactly the same as asking for the derivative at some point, okay? They are exactly synonymous. Now, to understand the limit definition of the derivative, we need to write out first our slope formula. So the slope between 2 points is defined as y2 minus y1 over x2 minus x1, right? Or more simply, delta y over delta x. So since this problem asks us to find the slope at x equals 1, let's start with our first point being at x equals 1. And we can pick any other point, let's say x equals 3, right? X equals 3. And we can find the slope between them via this equation to be something of that nature. Now what should stand out to you immediately is that this doesn't look like the tangent line. The tangent line looks something like this, right? That should be pretty obvious given our definition of the tangent line. So what we want to do in an attempt to make the slope between our 2 points approach the slope of the tangent line is move these points closer together. So let's pick x equals 2 as our new point and find the slope between those 2 points. And you can already see that the slopes are approaching each other, but they're still not exactly the same. Now what's important here is this. If we define this value as delta x, and we go over here and define it more specifically as x of the second point minus x of the first point, we can say that we want delta x to be as small as possible in order to get the slope of the tangent line. Now that should be a big hint as to what our limit's going to look like, because we want delta x to approach 0. We want it to be as close to 0 as possible without being 0, because if we say delta x equals 0, we now have 0 equals x squared minus x1, and then we have x2 minus x1, or x2 equals x1, which doesn't make any sense, because then you'd be finding the slope between 2 points which are the exact same point. That doesn't make any sense. Now let's go down here and redefine our slope as f of x2 minus f of x1 over x2 minus x1. Okay? Pretty straightforward, because if we see y as some function of x, where if you throw to it an x, it throws back a y value, this definition here and here should be pretty straightforward for your final and initial y values. Now, with this relationship that we have up here, we can say that x2 in fact equals x1 plus delta x. And we can substitute that into this relationship as well. So we have f of x1 plus delta x minus f of x1 all over the quantity x1 plus delta x minus x1. Now you should see again immediately that this x1 and this x1 cancel, and we're left with the simplified version of the slope between 2 points, f of x1 plus delta x minus f of x1 all over delta x. Now what we said earlier is this. We wanted delta x to approach 0. Now this is where the limit definition should be obvious, but if it's not, don't worry, let's write it out. The limit as delta x approaches 0, that means the limit as the space between the 2 points decreases of our slope, f of x plus delta x minus f of x all over delta x. And that right here is the limit definition of the derivative.